Good morning, everyone. We are really pleased today to invite you to the most recent event in our Tuesday at 2 series. Tuesday at 2 is presented by wastewatereducation.org, and the intent of Tuesday at 2 presentations is to introduce you to outstanding and innovative advanced wastewater treatment systems that also have a small community application. I am your moderator for the day. My name is Dendra Best. I'm the Executive Director of Wastewater Education, and you can see my contact information there. Do know that we are in the process of trying to obtain funding to provide closed captioning for all of our Tuesday at 2 events. But in the interim, if you do require a text transcript, just email me and we will send one to you. And a couple of disclaimers here that the purpose of our activities is we are intending to provide a forum for the free exchange of ideas amongst individuals and organizations. Our purpose is to form partnerships and resource networks for anyone who is interested in integrated water resource planning and management. Please be assured the information and conclusions that we present in these events do represent the opinions and the expertise of the presenters. These should not be construed as necessarily representing the opinions of or be perceived as an endorsement by wastewater education. However, that being said, we are really proud and pleased today to have a presentation by the Living Machines system, particularly Scott Nels. I think when you see this presentation, you'll realize why we're excited about this, as we hope you will be by seeing this event. And with that, Scott, I will turn it over to you.
Thank you, Dendra. Yeah, thrilled to be here, and I'm very, the work you're doing at wastewatereducation.org is fantastic, and looking forward to it. So yes, I'm Scott Nellis, Living Machine Systems L3C, and we'll jump right in. I'm going to shut my video off for the time being. I'll pop up here and there, but let's focus on the slides and the information here. So that's me. If you do need to contact me, you see my email address up there, snellis@livingmachines.com. Please feel free to contact me afterwards, and I'll be addressing questions as they come up throughout the presentation. So in terms of objectives, real quick we'll go through these, and it'll be somewhat free-flowing, but we'll follow the template. We want to understand the fundamentals of the water crisis, really to put things into context. Even if you don't see ravaged land, it might be coming to a town near you. So we'll understand the fundamentals of the water crisis, the advantages of these decentralized water infrastructure in context of the kind of current status quo, or at least the historical centralized systems, where bigger might not always be better. I'm going to raise awareness of decentralized technologies as a group. I'm going to explain how tidal wetlands work, look, and perform, and then I'm going to review successful water reuse projects and introduce the concept of sewer mining, and maybe most important, what is the sweet spot of reuse, meaning economically, where do the systems make the most sense? In addition, we'll hopefully have some time to, we will have time to walk through the water reuse planning tool, which I think will be very helpful and remove some of the mystery. It's complicated, but it's not rocket science. I will touch on some of the new regulations that might be moving east. It turns out that California, with Title 22 reuse standards, as well as some of the new ordinance, a new ordinance in the city of San Francisco, should be of interest, as many of the water regulations start west and move east slowly. And then we're going to touch just briefly on a recent EPA and WRF, Water Environment Research Foundation, kind of study as well. So please don't hesitate to ask questions if you have them. Let's start off with some slides, and the purpose here is to just put the water into context. So 25% of the terrestrial rainfall is co-opted for human use. That's a lot of water that we're taking out of the water cycle. 33% of nitrogen is also co-opted for human use. There are over 850,000 dams in the United States. Kind of an amazing number. Rainfall. I've been here already. We are basically, humans have radically changed life on this planet as we know. In a sense, we've replumbed the planet. So replumbing the planet has its consequences, and we'll talk about some of those in a moment. In 2012, 25% of the global population lives in areas that are defined as water stressed. And unfortunately, by 2050, the forecast is not looking particularly well, in that 50% of the global population will be living in river basin areas with severe and significant water stress. You add that to the fact that by 2050, over 70% of the global population will move into cities, again, concentrating the areas where water supply is stressed and the demand keeps going up and up. And of course, this probably does not relate to many places or any place in the United States, but it is a global problem, and there are a serious, or 93% of the population in a very large water study by Ocean of Blue suggested that 93% of the respondents rate water pollution as a serious or very, very serious situation and getting worse. So yes, freshwater shortages are here. They're not getting better. And in fact, even in the United States, in a 2008 Gallup poll, environmental issues, specifically water concerns, were ranked 1, 2, 3, and 4 as the biggest environmental issues understood in this Gallup poll. Interestingly, U.S., we spend $15 billion a year on bottled water. Just an interesting kind of water factoid. Kind of interesting when water is so inexpensive and clean in most areas, regardless for the forecast of shortages. Right now we have a water system, and yet we're spending $15 billion in the United States on bottled water. Another kind of context idea is that water prices, while they're relatively cheap in the United States, are going up an average of 9% per year. You throw a couple years and decades into 9% increases, and water will be a more expensive than it is. 25% of the global populations, yeah, we've discussed that. Where am I here? So this is the point, that with these water shortages that are beginning to happen in the United States, and this past summer has been particularly brutal on really the whole middle of the U.S., Texas as well, and yet we're only using in this country 0.3% of all the water that we use is reused. So there are tremendous opportunities to reuse water. In fact, even Coca-Cola and the largest companies are starting to realize and are now beginning to report, either demanded by their stockholders or by soon-to-be laws in many places, but from a risk management standpoint, even the Coca-Colas of the world are realizing that this global water shortage is significant and becoming more significant somewhat rapidly, to the point where it is affecting businesses' ability to predict and plan for the future. So the awareness is increasing, and it's wonderful that we're here today. And in summary of all this, this water mess is that the Earth looks like we'll have close to 10 billion people in a very short time. And the water supply is finite, as we know, and this graph shows specifically that even with increases in supply, basically finding new fresh water that we can use, we're not creating any more, but with the population increase to upwards of 10 billion, there is this forecasted very large gap between the amount of water needed for healthy lives, for our people around the world, but we're looking at a 60% gap in that supply and demand of water as this population grows, and that's quite significant, to say the least. And yet we feel, as a company and as an industry, we feel that there are technologies that address this gap, the 60% gap, and today I'm going to focus on reusing wastewater as one technology. And when I say reusing, I'll start by saying it right now that this is for our focus today is on non-potable reuse, not drinking water, but non-potable reuse. So we believe, as a company and as an industry, in the water reuse industry, if you will, that cleaning up wastewater to an appropriate standard to then be reused on site is a very viable, practical, technologically, I won't say easy, but the technologies all exist right now to consider reusing wastewater to guarantee a supply in your local community, and again, take a chunk, system by system, to address that gap. So I'm going to switch now a little direction here. Let's review the centralized model, the status quo, if you will, that was invented, so to speak, by the Romans. And it's a centralized model, and the most important concept related to the centralized model of water infrastructure is the once-through concept. So basically, the way it works in most places is that we have a source of water, whether it's upstream or it's surface waters or an aquifer below, and basically it's cleaned up to drinking water standards, and that's the only standard we have for the most part. Cleaned up, used once, and then flushed down the toilet. So you can follow these arrows, but the once-through model is clear here that we use water once, whatever we use it for, we flush it down the toilet, put it down the drain, never to see it again, at least not ourselves anyway. If you live downstream, you will see it again. So this is a this model, this centralized model, has been very productive. I mean, from the Roman standpoint, it's one of the things that made them great. They brought in fresh water via aqueducts, and they got rid of their wastewater via troughs in the street, and it did them very well. But we feel that after 2,000 years, it's time to consider another model that makes sense in light of these water shortages. So this is an example, this is an example that many of you are familiar with, an activated sludge municipal scale wastewater system. So that's kind of just closing in on that once-through model. Not particularly pretty. You surely don't want to live near one. They can be quite smelly. You don't use aesthetic terms to describe what happens in a centralized wastewater treatment plant. Which brings me to the decentralized model. So unlike the once-through model, the decentralized model has a couple different threads to it. One is that when we say decentralized, we're in a sense implying reuse. So the concept here is that once water has been delivered to a place, I thought I was active there. I'm trying to get my pointer working here. So once water is delivered to a place, is there a technology, is there a pragmatic, economical system to do something with that water on site, clean it up, so that it can be reused on site again? And that's the whole concept of a decentralized reuse system, an on-site system, if you will. But the point here is that instead of a once-through model, we're trying to be smart in that the water has been delivered to the property. So you might have heard that upwards of 50% of the cost of delivering water to your property, be it business or residential, is the transportation, moving that water from that centralized plant to your location, basically running pumps, pushing water through pipes. Can be very expensive with the associated in terms of electricity, and of course the associated greenhouse gases used to generate that electricity to move the water. So what's behind this decentralized reuse concept is that the water's been delivered. So what can we do on-site economically to prepare that water for its second or its new use, non-potable again. So you get the idea. Decentralized reuse has tremendous opportunities in that the water's been delivered, and it's now there are technologies to clean it up for reuse in a non-potable way. Which leads us to kind of the history and where those last slides in the last few minutes have been really about the context of the water problem we have. The technologies exist. We should start thinking about different ways, not necessarily the big pipe solution, but these on-site systems, and there are a variety of systems. But today we're going to focus from here on in on engineered wetlands. And there have been two, where did engineered wetlands come from? And I'm not talking about Mother Nature's wetlands, of course. I'm talking about wetlands that have been engineered to mimic what Mother Nature does naturally. So there have been two basic tracks, and for illustrative purposes, two basic tracks of the engineered wetlands evolution, so to speak. And one was from the traditional wastewater engineering groups, if you will, and the other is the wetlands engineering, which started out as wetlands and started out as hydroponic systems and lagoons and buckets of fish and plants. So these two tracks of research and pilot programs and installations have been happening concurrently for over 20 years. The result being, in the mid-2000s, emerging from these various these two tracks was the patented tidal flow wetland, which is what I do in my professional life in terms of the living machine. So that is a tidal flow wetland, and I'll explain in great detail in a moment what I mean by tidal flow wetlands. But the point here is that there have been multiple technologies that have been fine-tuned and are now available today, not 5 years or 10 years now, that have multiple projects around the country, very successful projects, and we'll focus on some of those. So let's talk about some of the key dynamics in tidal wetlands versus other decentralized technologies for wastewater treatment and reuse. So in the x-axis, the horizontal, we have the size of the system, the treatment footprint, and in the vertical or y-axis, we have the energy use. What is implied in this graph is that all these technologies, membrane bioreactor, activated sludge, textile trickling filter, aerated wetland, and tidal wetland and or living machine, we're assuming, and it's a good valid assumption, that all these technologies produce the same or similar quality effluent. So I'm not trying to make a statement here about this technology does a better job than this other technology. I'm just pointing out here that there is a footprint and an energy consumption side that's worth looking at across these technologies. So in the bottom, we have in the bottom we have an aerated wetland. That is an engineered horizontal subsurface flow wetland, for example, versus a tidal wetland. And if you notice where we are on the graph, that the tidal wetland system is considerably smaller, about 1/3 the size of a traditional wetland. That's part of the story. When you compare tidal wetlands to membrane bioreactors, mechanical systems, if you will, activated sludge, but kind of mechanized machinery, yes, they produce the same amount of effluent, the same quality of effluent in a smaller footprint, but they're not wetlands. They are not particular. Again, you don't use aesthetics to talk about activated sludge and membrane bioreactors. Those are very powerful machines, but they do their work kind of behind the scenes in basements, in structures, and so on. So from a footprint standpoint, tidal wetlands are very efficient compared to traditional engineered wetlands, and maybe a little less efficient in terms of space than the mechanized systems. But the real story is here on the energy scale. Tidal wetlands use approximately 25% of the energy of those mechanized systems, and I'll explain how that works and where that number comes from and why it is in a moment. But wetland systems are generally, or the new tidal wetland systems are generally smaller, and they're very efficient in terms of energy. To circle back around for a moment again, I think this slide was out of place, but the original hydroponic aquaponic technologies over here on the left side of your blackboard have been combined with these new tidal wetland systems that were developed by the TVA, the Tennessee Valley Authority, in the early 90s. And in fact, these two engineered systems and underlying technology have been combined today into the wetland, tidal wetland technology that I'm going to be showing you in a moment. So it's not the activated sludge, it's not the municipal centralized system, we're not talking about mechanized system for on-site, we're talking about a wetlands-based technology which combines both environmental engineering, information technology, traditional engineering, and more importantly, it all comes together in an engineered wetland, which is what we'll talk to now. So, any questions? Let's see, a couple questions came in, and I'm going to look at them and refer to the questions, hopefully in relative to the slides I'm working on. And I'm going to wait to talk about nitrogen and composting toilets. Questions have come in already, and I will address those at the appropriate time. So this is a process diagram for a living machine. And what we have here is a primary treatment, which is generally under the ground in a primary tank, and a couple things happen in this primary treatment. Actually, let me go through it quickly. So we've got a primary treatment, and I'll tell you in a moment. We've got what happens there. We've got a stage 1 wetlands. We've got a stage 2 wetlands. Notice the associated pipe assembly. The pumping system is in here. We also have a polishing module, and we have which includes filtration, generally chlorination, and we also have a reuse storage tank. So that's the basic flow, and let's talk about what goes on in this primary treatment. So primary treatment in this tidal wetland system has a few functions. The first is that there is a screen. So things that should not have been flushed down the toilet, plastics, inorganics, what have you, are caught here and removed on a regular basis. So there's screening. There is some settling of coarse solids in this primary tank. And, well, good time to address those. So the point is that 99% plus of solid waste is soluble. However, there is some settling of coarse crumbs, if you will. We generally suggest that these solids are removed between 1 year and 5 years. In that period, not monthly, not quarterly, definitely not weekly. So somewhere between 1 and 5 years. There are systems out there where this portion of the system has been automated. Whereas if there are sewers available, these systems can be designed and built so that there's an automatic flushing of these coarse solids, and that avoids the honey dipper, the septic guy, removing some of those solids again on that 1 to 5 year. So we've got screening, we've got some settling, and maybe most important, this is where, in this diagram, we've got flow equalization. This is a two-sided baffled tank, but in fact it's either a two-sided tank or separate tanks, but the function of flow equalization is important. It's not as if one flushes the toilet or puts water down the sink drain and that water then goes immediately into the biological reactor, the living machine. It doesn't. It goes into this equalization tank, and then the brains of the system will then dose the wastewater into these biological tidal wetland cells. What else? The pump module that I just referred to is actually quite a sophisticated module, generally outside the living machine cells, these wetland basins. And you can see it's a three-compartment cylinder, about a 4-foot diameter, and this pump module is taking its instructions from the PLC that's controlling all the flow in this tidal wetlands system. Moving through the system, as mentioned again, stage 1 wetland, stage 2 wetland, and I'll explain what I mean by wetlands and tidal flows in 1 minute. And then in the polishing, again, this is just a close-up. I mentioned that there is generally a carbon filter, chlorine dosing. Oh, I forgot to mention ultraviolet. So most systems, if there's anything other than disposal into the ground, will require some type of disinfectant just as a precaution, and the default disinfection technology for these types of systems is ultraviolet. If that water is then going to be brought back into the buildings for toilet flushing and or certain types of irrigation, and that chlorine dosing, a small residual of chlorine is generally required as well. So here's a picture of the vault, the disinfection vault, which is the UV. Here it's the ultraviolet lamp assembly that you can see looking down in this pump vault. This is a screenshot of a portion of the mechanical room in a project that I'll discuss at length in a few minutes. This is the San Francisco Public Utilities Commission room, and what we're looking at here, and I'll go through it quickly, is the water is entering, or put it this way, the sewage has been collected and run through the tidal wetlands and cleaned up, and now this is the mechanical room that has a flow meter here, a screen filter, a 50 micron screen filter. There is a turbidity sensor, and the reason for the screen filter and the turbidity sensor, as well as the cartridge filter, is to reduce turbidity down to really almost non-existent levels, so that the UV, the ultraviolet unit, can make sure it gets to all the bacteria, if there are any, and zaps them with that ultraviolet. If there is heavily high turbidity in the water, it's possible that the UV will not be able to do its job. In addition, to the UV, there's also an ORP sensor for that chlorine residual. And so what we've got here is the water is leaving the living machine and entering the mechanical room here, and is then cleaned up, monitored, chlorine is added, and then it goes into a water reuse tank, which is eventually the toilets and urinals are flushed with. So that's just one example of a mechanical room in an office building. But you might be wondering by now, so how does this living machine thing, how does this tidal wetland do its job? Well, here's the magic, so to speak. The point of wastewater processing is both to remove the nutrients, basically nitrogen and carbon, as well as make sure there are no pathogens in the water, bacteria. So while this is a continuous process, And I am asked, I see a note here about the hydraulic period in there. You can think in terms of upwards of 2 days that the waste is in there, but this is a continuous process, not a batch process. So imagine as if the process is just starting. So wastewater is introduced into the first cell, the first wetland cell or tidal cell. And the point here is we're trying to remove nitrogen, which in the waste stream arrives in the form of ammonium in liquid waste. So ammonium is positively charged. The wastewater is delivered to this cell, and in this cell is the fixed film ecology. This is where the tidal wetland differs from a lot of other technologies. So we have an engineered rock, which is lightweight expanded shale aggregate. It is a quarried product. This rock also has a slightly cationic or negative charge. So when the wastewater is introduced to this first cell, the ammonium is attracted to the surface of the rocks where the microbes, where the biofilm, where the fixed film ecology exists on the surface of these rocks. So the ammonium sticks to it. And then what happens is, and I've said tidal cycle numerous times, what happens is 12 to 16 times a day, the tide goes from high tide, meaning that that cell was full, to low tide, which is what we're looking at now. That cell is then drained. So biomimicry is the concept here. We are replicating what happens in tidal estuaries but nature does it twice a day, two low tides and 2 high tides a day. This technology has 12 to 16 tides per day. So back to the flow, the ammonium was introduced when the first cell was filled with wastewater, and then 12 to 16 times a day, that cell is then drained. The first half of the draining occurs by gravity, and then the second half, you've got an empty cell and a full cell. You open up the drain at the bottom, one equalizes to the other at halfway, and then the pumps kick in, which means that the only time living machines, tidal wetlands, are using electricity is during these cycle changes. And I'll come back to that on the energy side. But that's the chief reason why this technology uses so much less energy than those mechanical systems referred to earlier, and it's directly related to how oxygen is delivered, which gets me to the point, which is the cell then drains, and air replaces the water. Oxygen in the air is delivered through the voids, the spaces between the rocks, and the microbes, the biofilm, uses the oxygen and transforms the ammonium to nitrate, NO3. That's the beginning of the process to remove nitrogen, known as nitrification. When that cell is then refilled, again, 12 to 16 fill and drain cycles per day. When that cell is then refilled, the microbes have started chewing up the ammonium, and suddenly they've got nitrate, and they're eating, and they continue to eat, but there's no oxygen in the water, or I should say very little oxygen in the water. So to complete denitrification, the microbes strip the oxygen off the nitrate and the oxygen to oxidize, to continue oxidizing the waste, and what is released is nitrogen gas, N2. So to kind of repeat is that we've got NH4, ammonium, entering in the liquid waste stream, and what is released is nitrogen gas. And a similar thing happens on the carbon side, on the solid waste side. For every molecule of carbon in the solid waste from foodstuffs, there is a molecule of CO2 released. So what we have here is a system that takes in waste and releases nitrogen gas and CO2. No sulfides, no methane, no smell. Without those sulfides as well. This is another diagram showing another way of looking at what we just looked at. We've got wastewater entering the system. We've got the first cell that's being filled. The ammonium is attracted to the surface of the rocks. When that's drained, the microbes transform that ammonium to nitrate, and eventually when the cell refills, and again multiple times a day, that nitrate is transformed and released as nitrogen gas. And again, as I mentioned, the same thing on the carbon side. No methane, just low greenhouse gas contributed carbon dioxide. And then what we have here is the ability to reuse. So what comes out of here is tertiary quality water now, and that water can be reused for toilets, cooling towers, and irrigation. Any questions? Actually, there are a couple of questions. What about what about using composting toilets and treating greywater separately? The answer, I guess, is yes. Composting toilets are in the marketplace. I don't, and this is a personal opinion, I don't really see composting toilets being used in large-scale commercial or multi-family residential communities. But where they exist, well, there are a lot of places they do make sense in smaller operations, and theoretically, the liquid that leaves that composting toilet can be treated on site. But I have to be careful in implying that individual homes, that this technology is really available and appropriate for individual homes. While the technology works, the economics don't work. So the answer is yes, composting toilets can be part of the solution to reduce the water consumption, but personally I feel like they're somewhat limited in terms of the types of applications, single-family homes and a few homes. Other questions. What was the total nitrogen level that can be achieved? I'll give a quick answer to that, and then we'll come back to that very specifically. Total nitrogen generally in the effluent is generally around 10. TKN is below 5, and even if it's total nitrogen, that can be reduced further through the design and engineering of a tidal wetland system. This is just a picture of the control screen on the PLC, as well as this is the screen that the system operator would see on his smartphone. And again, it's just a screenshot of a touchscreen, but you get the idea that all the parts and pieces, the components, the various processes from primary to stage 1, stage 2, polishing, reuse, are all visually. There are visual icons introduced in the control panel, on the hardware of the system, and in all the documentation, just to make sure people realize what parts and pieces they're looking at. This is an example. If you hit the previous screen, if you touch the primary tank over here, and you get the next screen that looks like this, and it shows you actually what's going on in that primary treatment. It's an example of that logoed Stage 1 wetlands logo built right into the pump riser, or I should say the riser for the living machine access. So yes, we're trying to make it simple. We've been told that this new interface is probably the easiest interface in terms of these types of systems. Other questions? Let's see. I'm thinking of a small intentional community, 10 homes or less. The answer there is that, yes, it does make sense. It depends what the project dynamics are, but 10 homes starts making sense. For a tidal wetland system, there are other opportunities, I should say, other technologies that also make sense. But it's important to mention, and I'll show this in pretty strong graphic terms, that when systems get bigger, there are significant economies of scale, and when systems do get bigger, they tend to be more economic. They have a quicker economic payback. So yes, 10 homes might make sense, depending on the project dynamics, but surely the technology works. This is I'm going to move to some projects where tidal wetlands have been installed. This is the Port of Portland at the building. It's the Port of Portland is the Marine and Aviation Management for the Portland, Oregon Airport. This is their headquarters building. It is a LEED Platinum building, and they have a wastewater treatment plant that you're looking at in the lobby of this 2-year-old headquarters. It was commissioned in June of 2010. So here you have the indoor lobby, which is the stage 2 wetlands, and right outside that indoor lobby on the outside of the curtain wall is the stage 1 wetlands. The decision to put a portion of the system indoors was a design decision and not a necessary decision. So this was purely the design team, the architects and landscape architects chose to put a portion of the system in that lobby. I see I have a question here about systems in cold weather. Tidal systems, or any wastewater systems for that matter, cannot freeze. So the answer in terms of what locations these systems are suitable really depend, not just on the nighttime ambient temperature in the coldest part of the year, but also the size of the system has an effect. The concept being that thermal mass, meaning, say, for example, 50,000 gallon a day system at 50-degree wastewater has a lot more thermal mass and heat carrying capacity than a system, say, at 5,000 gallons a day. So in terms of climate, wastewater systems cannot freeze. Having said that, there are a variety of engineering tools that can make these types of systems work in very cold climates. One of those technologies would be a horizontal subsurface flow wetland, and there's a pretty strong project suite for those technologies in very, very cold areas. There's also supplemental heating available for the coldest days of the year. Depends on the cost of energy and what's available. And also, sometimes these systems are put in greenhouses on site where the wastewater systems becomes a showpiece as well as a productive wastewater treatment and water reuse sourcing plant. So that gives you an idea in an urban office building what a tidal system can look like. In terms of the treatment performance of that particular office building, this data was third-party data over about a year and a half, and it shows that the influent BOD in this building averaged 160 milligrams per liter influent and less than 2 effluent. On the TKN, averaging 134, that's total key nitrogen, milligrams per liter, and coming out of the system at 1.2, and total suspended solids. You can see it there. So as I said a few minutes ago, the treatment performance of wetlands are on par with any on-site systems and technologies that are available in the market. Moving along, this is a rendering of a project that has since been built. It is in downtown San Francisco. It is the Public Utilities Commission. They are the water, sewer, and power authority for the city of San Francisco. And this is their brand new headquarters. You can see City Hall in San Francisco. Well, this is a rendering. Yes, it's been built, as I'll show you. But we've got a wastewater treatment system in downtown San Francisco for the water, sewer, and power authority. 950 people in that building. This is what the building looks like, and the flow is, there is a primary tank in the, actually for illustrative purposes it's here, but in fact it's in the loading dock around the corner here. So there's a primary tank, there's actually a trash tank, there is a flow equalization tank. The brains of this tidal system then introduce that wastewater to the stage 1 wetlands, known as number 2 here. After a period of time in the stage 1 wetlands where we have cell A and B, meaning we're filling and draining alternately in that stage 1 wetlands. Interestingly, the majority of the BODs are removed in the stage 1 wetland. But if you notice, the system has a stage 2 wetland, and that's where most of the, or the majority of the denitrification takes place, and then there is a water reuse storage tank. This is the system I showed the mechanical room for a few minutes ago. Now I'll show you the living machine. So this is that stage 1 wetland. It is outdoors under the building eave. Again, we're talking about a couple blocks, a block and a half from City Hall. So we're looking at a stage 1 wetland, reciprocating wetland back and forth multiple times a day, after which it is pumped to the Stage 2 wetlands, and Stage 2 wetlands has a couple different pieces actually. This gentleman sitting here doesn't realize he's sitting on the edge of a wastewater treatment system, and again, this is the beginning of the Stage 2 wetlands. So we've got cell 2A where this guy is sitting, we've got cell 2B here, and then we have cell 2C, which is further down the street, the sidewalk side, which is actually an outdoor as well as an indoor system. So let's just stop for a moment and realize what we've got here. We've got an office building, a brand new office building, 950 people in a downtown urban area, taking all that waste from 950 people, which, by the way, is only about 5,000 gallons a day with low-flow fixtures, processing it in this series of wetland cells, and then going to that reuse storage tank in the basement, and then being pumped back for toilets and urinals. Kind of exciting. Moving along, this is a project that was done in Las Vegas for a animal shelter. And I like this graphic, and it gives a real clear view of that rock media. And I'm going to come back here and talk about that rock media. I touched on it a few minutes ago. So this is lightweight expanded shale aggregate. It's the properties, the negative charge, the fact that it's porous, the fact that the microbial community loves this habitat, which is where this ecology, this fixed film ecology lives. So there is no soil in these systems. The plants, while we don't recommend it monospecies here, this is a little risky in terms of pest control. It was hit with insects, but there is no soil. So many types of plants can grow, but they can't be plants that need soil. But there's no shortage of the types of plants, and the plants contribute to the both the nutrient uptake, basically to the nutrient uptake as well. Although the majority of the work is done by the ecology sitting on the rock surfaces. You'll also notice that this containment unit, or this tidal cell, or this box of rocks, in this case it's a CMU with a topper. These containment units can be made out of anything. Of course, they must hold all that water and hydraulic pressure, but they can be everything from earthen containment to clad in marble or granite that you saw in that Portland project. Moving on, this is another example of a tidal wetland that is partially outdoors and partially indoors in a classroom. Interestingly about this project, that the effluent quality was so high that there is this system has a permit for on-site surface disposal in a national park. So this is a K-8 school. All the wastewater from that K-8 is processed in this series of wetlands, both indoors and outdoors, and the clean effluent is then disposed of on-site, on the ground, which then flows into the Cuyahoga River in a national park. That is quite amazing to many wastewater professionals, that there is a permit for surface disposal from an on-site system. The system's been running since 2007 flawlessly. This is another example of a wetland, tidal wetland system, a living machine. It happens to be on the Pacific coast, and I show it. It's a better example of a variety of native plants as opposed to that monospecies. And it also shows you that, again, the containment units can be built out of anything. Here they chose to use the same raw concrete material that were used in other parts of the site, including the mineral springs and so on. Been running since about 2007, I guess. Moving on, this is another tidal wetland system. This is in Greensboro, North Carolina, where I reside. So we are looking across the tidal wetlands, across a stormwater management area, onto a irrigated baseball field. So this system takes all the waste from both the middle school and the high school. Well, let me back up here. So they are collecting rainwater from the roofs of the high school that you're looking at, as well as the middle school, which is behind the camera. That wastewater, or I should say that harvested rainwater, is then stored in a cistern below the basketball court that's off that you can't see here. That water is pumped from the cistern to the toilets and is flushed into the living machine, and all that waste is used for subsurface irrigation for a variety of athletic fields on this public school campus. I also use this as an example to point out this lovely 6-foot chain link fence. This is was demanded by the regulators, and I find it interesting that we had another project in Virginia for a high school, and rather than wanting to sequester the tidal cells, that particular design team has requested that the tidal cells be in the forecourt of the building so that the students could sit on and congregate around. Just a kind of an interesting and different regulatory approach, since there are no national standards. Wherever these systems are put in, working with and through the project team and the design team working with the local regulators is the part of every project. This is a rendering of again, you're looking at a wastewater treatment plant, not exactly what one would think. This should be built in 2013. It's for the Tijuana border the U.S. Customs House at the Tijuana border crossing, and you'll see, or I should say, what is in these cells, that the containment units or cells are. In this case, they're designing them with the Gabion rocks, and you normally, I don't think many people would look this, and even given a multiple choice question, would answer that this is a wastewater treatment plant supplying water to be reused for the toilets and cooling towers. This is a project that is in the ground now. Sorry, I don't have updated pictures. In fact, grand opening is today. This is the Marine Corps Recruitment Depot in San Diego. This was an existing monument, a drill instructor monument at the base, and this is a sewer mining project, in that rather than taking the waste from a particular building, a pipe leaving one building, here they cut into the sewer lateral, the sewer main, if you will, and are dialing in 10,000 gallons a day, which is cleaned up in this tidal wetland, which has been put around, built around what was the existing hardscape. So the monument was here. The planter boxes, the living machine, the tidal wetland boxes, were put in after the fact, again, taking 10,000 gallons a day from the waste stream and using it for irrigation of this kind of ceremonial site, if you will, this drill instructor monument. This is another rendering of a mixed-use, very large residential project that's going in the panhandle of Florida. And this vision picture, it really addresses kind of the community approach, whereas there is no infrastructure, water and sewer infrastructure in this area. There are 12,000 military families moving into the area, and this developer is trying to create not only a whole community in a town center, but do it very ecologically and respective and realistically managing the water. So what we have here, where these people are sitting, in the middle here, that is the wastewater treatment plant, the tidal wetlands, taking the waste from this mixed-use area. There's an amphitheater here. There will be upwards of 900 people. And the wastewater, the cleaned up effluent, will be pumped back into the buildings for toilet, as well as for this wetlands, kind of the disturbed wetlands area that needs to be rehabilitated. So this is an example where without infrastructure, local decentralized wastewater processing is very appropriate, as well as it helps recharge some of the impaired wetlands. So that's something we're going to be seeing more and more of. Another thing about these systems, this is gives me an opportunity to talk about, residential systems that are built out over many, many years. One of the negatives about the centralized systems is that you build technology for 20, 25, 30 years ahead, and you build that all now, and eventually the capacity will be needed. But in these on-site systems, it's very possible, or I should say it's very appropriate, that the systems are modular and that they're built to grow along with the community growing. So this particular, sorry for the lacking pictures here, but this is a project, a residential neighborhood. It happens to be a low-income housing area in the called Quan Lama in the off the coast of Seattle. And eventually there will be 40,000 gallons a day when the whole community is built out. But for right now, it's taking up a little less than 7,000 gallons a day. So the whole sewage, tidal wetland infrastructure does not have to be built up front with all the associated costs, as long as it's thought of and designed and planned for the future, as, for example, the 60 unit in this commons, as, for example, these 60 units are built, they will be building additional tidal cells to handle the increased capacity. But that's really a way to manage infrastructure expenditures over a longer development time than putting it all in up front. Let's see what other questions have come in. Question about forced bed aeration. This relates to cold weather systems. I mentioned that there are these horizontal subsurface flow wetlands, and the question came in from Rodney about is the technology that Scott Wallace, who's the guy up in Minneapolis, promotes and designs with, is that technology combined with this wetland, or I should say with this tidal wetland? The answer is no. We're familiar with each other, and again, those systems are better in very, very cold climates where putting a system inside a greenhouse is not viable or requested. Let's see what other questions have come in. I talked about nitrogen. I think it's time to move on to the planning tool. So what I've done here is captured a whole bunch of screenshots to show a water reuse tool that is available. And if you'll let me know, I'll be more than happy to give access to you for that tool. It is a web-based Google Doc, but I'll give it to you in these screenshots. So the first thing is to the first thing in terms of trying to run a project scenario in order to find out what's it going to cost, what's the payback, what's it going to do, how big is it, what does it look like, and so on. So I'm going to walk you through somewhat quickly a series of screenshots that were just captured from a live water reuse scenario. So the first thing we did was we told the system, you can see a drop-down menu here, but basically we told the system that the project is in Pittsburgh, and in fact Dendra gave me some of these project dynamics. So what we want to do here is we have a choice of the water sources, but we're going to keep it simple, and we're going to collect wastewater, and we're going to consider using it for irrigation, consider using it for toilet flushing, and then I have just kind of a wild card, other water reuse possibilities. And also we're treating black water for reuse, the highest standard. Again, this is not live, but if I click down this menu in the real tool, you would see that in addition to black water treatment, there is gray water treatment for reuse as well as black water for disposal. There are 4 different types of effluent quality that you can dial in here. So we basically said, we've got a project in Pittsburgh. We want to collect wastewater. We want to figure out if it makes sense to use it for irrigation, toilet flushing, and some other means. And we're going to make it black water for reuse. So what we did here is we took a real scenario, and we're now in the source loading portion of the tool. And what we said is that we'll have 30 employees on this site and in an office building, and 40 employees in a retail store, and 150 seats restaurant, and 20 hotel rooms, and 250 students visiting, plus there's a visitor center and even a camp. Again, it's a little theoretical, but my purpose here is to give you an indication of how the tool works. So all those uses by that 30 people, 40 people, etc., have a different conversion factor, meaning in general office space, one person does not use as much water as they do at home. So the total, and I'll give you I'll open up the thoughts and the table beat that's driving these numbers, but for what we have here, that's 9,500 gallons per day. Maybe more importantly than that is the fact that the system tells us that it's 11.5 kilograms of BODs per day and 3.6 kilograms of total key-joule nitrogen per day. And in fact, that's what these systems are engineered around. Flow is very, very important, but most important is the actual loading and to make sure that there is enough capacity in the tidal system to handle that wastewater load. So in addition to those commercial parameters on this theoretical project, we also said 540 bedrooms. And that 540 bedrooms accounts for 54,000 gallons a day. So the total project that we're trying to get a feel for here is 63,500 a day with the associated loading of biomass loading. So then what we do, the system tells us that if the cells are 7 feet deep, we will need 1,111 square feet per cell. So I've gone in there and basically said 40 by 28 is pretty close, so we get 1,120 feet per cell versus 1,111. That's very accurate or very close, and we've done the same thing for stage 2. So you might not know this, but the system knows that when we want to treat blackwater to a reuse standard, it will take both stage 1 and stage 2 treatment, and I did the same thing here with in terms of designing the rectangles, the boxes, the tidal cells. You can change the 7-foot depth. That is the default for the system, but we have designed systems that are deeper and therefore smaller in footprint, as well as shallower and larger in footprint. So we basically said this is the wastewater source of this property. And the summary is that it's 63,000 gallons a day, and you saw that already. All right, so we've defined the sources. To give you some insight, where did we get those numbers from? So, for example, general office space. Our experience, as well as a combination of Metcalf and Eddy textbooks, and our experience basically says that with new low-flow fixtures, we can expect 5 gallons per day per employee in an office setting. That's based on an 8-hour FTE, full-time equivalent. If there were 2 shifts or 3 shifts, you would triple that or double that or triple that. Notice also that with general office space, that the BOD count is actually quite high. And it makes sense because most of what leaves an office building is sewage. So between the TKN at 160, this and the BODs at 300 milligrams per liter, general office space is what's known as a highly concentrated wastewater stream. Compared to, for example, on a per bedroom basis, it's 80 on the TKN and 230 on the BODs, and that's because this is a residential situation, and residential, of course, includes, in addition to toilet, but bathing and laundry and cooking and washing and all the kind of large dilution factors. So the tool shares with you what these conversion factors are and the associated waste flows and loading constituencies. So we're done loading the system. Now we're saying, well, we just said we're going to reuse the water. So for this example, we've got 100,000 square feet. You have an option in the tool to have multiple zones with different landscape coefficients. And if you remember, we set this up for Pittsburgh, so you'll notice that there is, this is the daily gallons per day in monthly buckets. So in January, the daily 100,000 square feet in Pittsburgh can handle 1,700 gallons a day. That is subsurface irrigation. That's obviously not a lot going on in January, but we can still get rid of a little bit of the water that we've cleaned up in this theoretical example. By the way, that daily demand in gallons goes to 10,000 and change in June and July during the growing season. So we defined the source of the wastewater and the parameters of that wastewater. Now we're defining the reuse, and here we're looking at irrigation. In addition to irrigation, we're going to plumb the toilets. In this case, 300 of those people, we're going to plumb the toilets with that reclaimed water. And then to be cute here, just to make sure the teaching moment works, I'm saying there's another 10,000 gallons per day of non-potable reuse opportunity. And keep that in mind, because again, I'm trying to show you how the tool works, but that could be cooling towers, that could be truck washing, dust control, and other kind of secondary water reuse opportunities. So we get an incoming water summary, which says we've got 63,000 gallons a day of blackwater. There's a little bit of surface infiltration, and that's what the water that's available. And this is what this particular, this is the water balancing slide that shows in bar graphs the supply of 63,000 gallons a day and the demand, which is considerably less because it's only toilets and a little bit of irrigation and that 10,000 gallons a day of other. But again, for teaching purposes, the goal here is to balance the supply and demand and as closely as possible, knowing that it's never perfectly balanced, because generally in North America we get the rainwater when we don't necessarily need it for irrigation, meaning we get it in the winter when we don't need it, and we don't necessarily get it in the summer when we can need it. But again, it is regionally specific. But here we have a situation where we have a lot more supply than demand. But this is realistic in my day-to-day. It's very often that we have the supply and not necessarily the reuse, and to make the systems as economically as possible, your demand should be as close to your supply as possible. Moving along, we then get a cost estimate, a set of costs. And again, this is a theoretical product, but the system is 9,000 square feet, a little under a quarter of an acre for 63,000 gallons a day. You can see what the effluent quality is for BODs and turbidity. You can see what one section, in this case the living machine, what that portion costs, and then you can see what all the portions cost. So you've got the system construction, you've got the primary treatment, you've got the disinfection system, you've got the engineering cost, you've got the oversight commissioning costs, and so on. So somewhere in grand total about $1.1 million to $1.3 million is what a 63,000 gallon a day system would cost. And interestingly enough, and this is probably the most powerful part of the tool, that again, we're working with screenshots here, but what's the life, what does $1 million or $2 million mean relative to the cost of water in the volume? Do you get an economic payback? So the tool allows you to put in the cost of money. Here it's 5% discount rate. What is the cost of water? This is really, really low, this $1.50, but I took it from Dendra, and we'll use it as a real-life example. So water is $1.50 per HCF. Sewers is $1.50 per HCF. The projected inflationary factor for increases of water and sewer are 9%, and this is a big one. So, if for this particular theoretical example, the idea is, do they hook into a faraway traditional centralized system, or can they avoid those costs? In this case, the avoidance costs are $875,000, which will have a significant effect on the ROI, or on the payback. So while water is cheap and sewage is relatively, very inexpensive compared to other parts of the country, we still have a lot of water we can use, and we might be able to avoid $875,000 in sewer connections for all those units, all those residential units. In addition, we plugged in $40 per month per household for the wastewater treatment, and so that's a revenue, if you will, of $168,000 per year. And we also put in a $20,000 per year employee to operate. Generally, these systems they need about 4 to 5 hours a week to operate, and hopefully it's a staff person, depending on the type of project and community, that can do that. If not, there are third parties and companies that can do that. So we put in all the sources. We put in the potential reuses, some of them. We don't have a balanced system just yet. We then plugged in the cost of water, the cost of sewer, the avoidance costs, and what it comes out to is that the system basically average cost about $1.2 million, and here's the interesting thing. Because of that give back, or I should say that avoidance cost of $875,000,
and again, I'm not making a statement here that this is, this is budgetary cost estimate. I'm showing how the tool works, but it's a fantastic tool in the sense that with that avoidance cost of $875,000 plus $168,000 a year contributed by the user community for this system, the payback is less than 3 years considerably. Again, this is theoretical, but I'm trying to show how the tool works. In addition, the tool actually shows what the components of such system would look like, not to scale and size, because if you remember, I did give you a size. It was about 8,500 square feet of above ground footprint, 8,500 square feet of these cells. But again, the tool here shows you a process diagram for a two-stage reuse system. With reuse, if there was no reuse, this is the reuse tank, then this would just be a straight pipe into the ground. And the summary sheet in the tool basically says that at 63,000 gallons a day, that's 23 million gallons, roughly 23 million gallons a year, we've only found a home for 6.2 million gallons a year in terms of the reuse opportunity. So that's a big opportunity, but it's not necessarily a deal breaker in terms of a payback because of those avoidance costs as well as some of the revenue earned. And the difference in these numbers of 6 million and 23 million is really disposal. So that we're going to have to do something. The system is going to have to be designed to dispose of, if we can't directly reuse in non-potable form, a disposal system in the ground. And there are a whole variety of disposal systems, and I understand that Tuesday at 2 sessions have talked about distribution systems in the past. So lots of opportunities to find something to do, but nonetheless, we have a wastewater treatment system that can avoid the heavy costs associated with hooking up to the municipal plant and the greenhouse gases associated with doing that, moving water long distances. And again, in this theoretical example, there's about $1,600,000 savings in just the first 10 years. Any more questions? I'll click my video back on and see if we've got any other questions. And I'll say goodbye now, and I'll look online here to see if you do have questions. I'll be here for a few minutes. Moving right, you know what, I didn't see what I did here. You know what, I didn't finish, so let me continue. I have a couple more slides, and this is an important one, but the timing is good in that what I just exposed there, that there is a strong connection between the payback period and the volume of water as well as the cost of water. So that example had a large volume of water, even though not that much was being reused in that design. And even with cheap, inexpensive water, the givebacks, meaning the avoidance costs, made the system work economically. But in general, assuming for the moment that there are not avoidance costs or revenue generated, I think I can make some general statements about scale and payback. And here are the general statements. So while this is in liters, you can divide by 4 income gallons, so this is roughly 25,000 gallons per day. At 25,000 gallons a day, the cost of the system will result, and the payback is about 8 years. But notice the shape of this curve. Notice this is really important. At 400,000 gallons per day, or roughly 400,000 liters per day, roughly 100,000 gallons per day, we're looking at paybacks routinely under 4 years, in some cases under 3 years. The formula is simple for the payback. You have a capital cost, and then you have a recovery cost based on the water that you're reusing. So it's the gallons being reused per day times the cost of water and times the cost of sewer times 360 is the recovery of that capital cost in a year. Roughly speaking, of course, there's the time value of money and so on. But the point to remember here is the shape of the curve here. This is showing economies of scale. Larger systems have dramatically quicker payback. What else? This is a picture of a large 200,000 gallons per day tidal wetland system at a zoo in the Netherlands, and you can see how healthy the plants are. They are indoors. Tremendous feeding of the plants from that wastewater, which is below the surface of the rocks. This is another picture of a tidal system indoors at Furman University, and it is part of the environmental education curriculum. It's a living, working classroom and wastewater treatment plant. And just finishing up with a couple, this is a rendering. It's a beautiful rendering of a combined integrated water management system on a college campus. So these circles, these cylinders or cisterns are to store the rainwater coming from the roof of the building, and surrounding those rainwater cisterns are these individual asymmetric tidal wetland cells, which are the blackwater wastewater treatment plants. I just think it's interesting, and again, I mentioned a few times that these tidal wetlands are part of the site aesthetic and add to the beauty of the site, and are not something that necessarily needs to be hidden away. Again, no smell. These boxes, these tidal wetlands can look like anything, as you can see here in this rendering. Here's another view of that shot. So we've got a wastewater treatment plant in the quad along with a rainwater storage system. Thank you very much, everybody, and I really appreciate your interest. My email is up here. Please do not hesitate to contact me. My phone number is here as well, and I thank you, Dendra, for the opportunity to present to your group, and the work that the wastewatereducation.org is doing is fantastic. There are a lot of opportunities. Technologies exist. Expertise exists all over the country. And that's the purpose here, to show that these are no longer systems that are out in the future. It all exists for professionals right now, here and now, to start thinking about decentralized reuse systems. Thank you.
Thank you so much, Scott. I think anybody who has sat through these slides will be absolutely amazed at what's possible, and the idea of sustainable integrated water management, including wastewater, is really what our focus is this year. We recently published our 2012 through 14 strategic plan with a very simple theme. It's all connected, and it is. You will see my contact information there again, our website. You'll also be able to find us on Facebook, Twitter, LinkedIn, YouTube, where this video is being posted. And we recently started a Pinterest board to put our favorite projects and organizations out there in the public spotlight. Again, do email us if you would like a written transcript. And as a nonprofit, we do rely upon support, sponsorships, donations, and grants. So if you have found this presentation to be of value, we really would appreciate your support, either in the form of a donation, or on our website, you will find the little web logo that you can display in your emails or on your own website as a link back to us. And it features our water droplet and the information that we are a WaterSense, EPA WaterSense partner. And one of the points that we didn't really have a lot of time to go over today, we were running a little long on time, is the excellent work done by the Water Environment Research Foundation. There is an organization, an umbrella overall organization for the Decentralized Water Resources Collaborative, and I did put the web link into the chat window, and let's just quick take you to that website. Okay, and on your screen there, you will see the Decentralized Water Resources Collaborative website. I see some of the images aren't loading. I think that's because it's a flash-based system. Underneath here, oh, there they are. They just arrived. You will see that they're separated up into various categories for on-site individual systems, for neighborhood cluster systems, green stormwater infrastructure, watershed scale solutions, and for urban applications. And I think you'll notice that in Scott's presentation there were several urban applications. And if you scroll down that page a little bit, you'll see there are a whole bunch of different resources, case studies, and certainly we do encourage you to go take a look at, particularly that question that arrived for cold climate. And as Scott mentioned, that all wastewater is inherently warm, and it will keep its hydraulic temperature control for a certain amount of time, and subsurface, those systems can remain active for a very long time. I do refer you back to a prior Tuesday at 2 presentation by Rodney Riskin of GeoFlow, which was about subsurface treatment in cold climates. And I believe, Scott, that you sat through a couple of the WRF recent webinars, and I think those are available on the WRF website.
Yes.
Yeah. So,
in fact,
go ahead.
Well, if I could, there was a recent webinar that I sat through with discussing in detail the MOA, the Memo of Understanding between the EPA and the WRF collaborators, and it's very interesting. There has been a lot of the gist of that webinar was similar, if not totally parallel, to what we're saying here, is that the decentralized technologies are here and now. So please work with your local firms and engineering firms and your partners and ask for these, quote, alternative systems, because they're becoming less alternative day by day. But when we hear the EPA and WRF talking about these systems, that's a very strong message that this is not out in the future anymore.
Okay, and I'm just putting the WRF URL into that site, and I put that up onto the web tour window as well. So again, quick shout out there for WRF. So going back to our closing slide, if there are no other questions, excuse me, I think we will close for the day. Thank you, Scott. We hope to have you back again with some more updated information of new systems that your company is putting in. Bye-bye.
Thank you, Dendra. Thank you, everybody. Bye-bye.